So my name is Xudong, and I'm from Zhejiang University in China. On behalf of all the authors, I'm giving the presentation today. So first, let me talk about the motivation of this paper. We are mainly doing research in signal processing of gyroscopes. This is a whole picture of a typical gyroscope system. It consists of two major big loops, one for the drive mode control and the other for the sense mode control. Normally, for the drive mode control, we use an adaptive gain control loop to regulate the amplitude of the gyroscope drive vibration to a fixed value. And also, we use a phase locked loop to track the real-time resonating frequency of gyroscope drive mode. So it is very important to gain the precise amplitude and phase information for gyroscopes. For the sense mode control, we normally have two loops, one for the quadrature error signal and the other for the in-phase input angular rate. For the phase and the amplitude information in gyroscope drive mode, it is very important to gain a very accurate and precise phase and amplitude information. Here is why. Because phase errors cause the actual working frequency to deviate from the real resonant frequency of gyroscope drive mode, and it could cause quadrature leakage between the quadrature channel and the angular rate channel. For the amplitude signal, amplitude errors causes the actual working amplitude to deviate from the reference value. So it is one of the error sources of gyroscope scale factor. So it is very important to gain the precise phase and amplitude information. How bad is the quadrature leakage? Here are a lot of gyroscope experts. So I'll do a small calculation. For a typical gyroscope with a quadrature error of about 50 degrees per second, a 0.1 degree phase error could cause a quadrature leakage on the order of 300 degrees per hour from the quadrature channel to the angular channel. So it is unacceptable for a high precision gyroscopes. It gets worse because often the phase error is determined by temperature. It is a slowly varying term, so they call this large gyroscope output drift. So we have to emphasize that phase information for gyroscope drive mode is very important. How to reduce the influence of quadrature error leakage? Of course, we can do quadrature error nulling using dedicated electrodes. This has been done. And another way to do is directly compensating the major phase errors for the drive velocity signal. This paper mainly focuses on the second method. However, these two methods are compatible with each other, so you can combine these two methods together to get better performance for gyroscopes. So we want to gain a very precise indication for gyroscope drive mode amplitude and phase. So we have to analyze which is the major phase error source. Nowadays, most of the signal processing are done in the digital domain, except the analog interface circuit. We can't do it all digitally. For digital signal processing part, since as long as the reference voltage for AD converters and DA converters and the sample range does not change, it produces a fixed phase shift. But it is not the case for analog interface circuit because the phase and amplitude response of the analog interface circuit varies with temperature, which is which is a major error source for gyroscopes. So let's talk a little bit about a typical capacitance-to-voltage circuit. In order to avoid low-frequency noise, the capacitance are modulated with a high-frequency carrier wave, and then demodulated to the baseband. Here is the signal spectrum. This is the gyroscope drive displacement, and it is converted to capacitance, and the capacitance is modulated with a carrier wave. So the information now lies on the two side bands. In order to extract phase and amplitude information for gyroscope drive mode, so there are two simple structures. One called a double sideband configuration, single sideband configuration. But it is a little bit different from the textbook. It includes the modules to extract the DC signals. For DSB configuration, we're using a two-step demodulation process. First, the signal is demodulated with a carrier wave with the frequency omega c, which converts the capacitive signal to baseband. And then this baseband signal is demodulated with a pair of quadrature reference signals to gain the amplitude and phase information for gyroscope drive mode. And for the SSB algorithm, only one step of demodulation is needed. We directly use the information of one of the sidebands and demodulate it with a pair of quadrature reference signals. We use the high frequency omega c plus omega d. So we can directly acquire the amplitude and phase information. In this paper, we propose a modified double sideband demodulation. We only did one step demodulation. However, we used both information from the sidebands. So besides the high frequency sideband, we also did demodulation for the low frequency sideband. And this information are combined together to obtain a total indication of the amplitude and a phase indication of the phase. Here are the theoretical results. As you can see from the table, for DSB algorithm, the amplitude information is dependent on interface circuit phase delay. And for SSB algorithm, the phase we acquired is totally determined by theta CV. But for the MDSB algorithm, we propose both the amplitude information and the phase information are totally independent of theta CV. So let's talk about the side effects of DSB and SSB algorithm. For DSB algorithm, because the amplitude information we acquired is dependable on theta CV, so the amplitude deviates from its reference value, which could cause scale factor errors. For SSB algorithm, because the drive frequency deviates from its resonance value, this could cause quadrature error leakage into the angular rate channel. Here we present some test results. This is our test board for our gyroscopes. This is a parametric packaged gyroscope, and this is the analog interface circuit, and this is the digital signal processing PCB. This is the characteristics of the gyroscope we use. We did tests for we managed tests for gyroscopes, the same gyroscope using DSB algorithm and using MDSB algorithm, and we tested each for 2 times. As you can see from the test results, this is all done from code state that the power on effect is substantially reduced compared to gyroscope using DSB. And not only did we improve the power on process for gyroscopes, but also using this new algorithm, we can acquire the exact theta CV information. And this is also recorded for 2 hours using MDSB algorithm. So you can see that the theta CV information is very similar to the gyroscope power on process. So this information could be used for further compensation. This is the end deviation analysis results for 4 groups of data. As you can see, the angle random walk stays the same for these 4 groups of data, but the bias instability is substantially improved by about 3 times. This is mainly due to the improvement of more accurate amplitude and phase information we gain. To conclude, we propose a MDSB algorithm to extract the amplitude and phase information for gyroscope drive mode, which is independent of the interface phase delay. And also, the exact phase delay of the interface circuit can be extracted in real time, so it can be used for further compensation. This hasn't been done yet, but we are going to do that. The gyro bias instability using MDSB is substantially improved by 3 times compared to that using DSB algorithm. And in the future, we are going to apply this algorithm to the gyroscope sense mode, but we hope to gain better results. And that is all. Thank you.
Thank you.